So now let's go over to talk about hotspots and data races, which are important concepts in parallel programming. So hotspots is the things that you want to look for when you want to parallelize a program. So these are blocks of code that consume a lot of CPU cycles. That's where the program spends its times. So this is the target, the first target you want to look for tuning your code, whether it's sequential tuning or it's parallelism. In particular, it indicates typically where your application is not parallel, and you find it by sampling the execution of the application. And to do that, you use tools. You can do it on different granularities. You can do it on a process level, on a function level, source line base level, source code line base level, or basic block level. And once you're found a hotspot, there are many ways to tackle it. You can change your algorithm, you can parallelize loops, you can do task decomposition or architecture-specific refinements and so on. Not all hotspots can be removed, so if your program do inherently spend time in some part of the program, it might be so because the algorithm is designed in such a way that it has to be that way, or that there are hardware limitations like memory bandwidth or whatever that prevents removal or improving the hotspot. So the way to locate a hotspot is to use a profiler. So learn how to use a profiler. There are some simple profilers included in Linux, for instance gprof or gcov. Gcov is sort of a later version of this. I will not really go through how to use it. You have to read the manuals and so on. Basically, you need to compile without optimization, and then you need to tell the compiler that you want to be able to use a profiler. And in GCC, most probably the flags you need to do is -00, and which turns off optimization, and -G, which emits information that are useful for a profiler. So gprof and gcov are the most sort of simple ones. Gcov is quite elaborate. You can get a lot of information, but still these are the sort of the basic ones. oprofile is a free system-wide profiler. It's typically used when you want to measure the whole sort of system, many applications, not only a single application. So it samples what happens in the system when you. So it's useful when you want to profile kernel also. The latest tool from AMD is called AMD CodeXO. It's a free debugger and profiler. It can also be used for GPUs. So this is sort of what they sort of promote in order to use their fusion architecture, where they have added a GPU on the same chip as the CPUs. And then you have the Intel VTune or amplifier, which it's sometimes called amplifier, from Intel, which is a powerful profiler. You can get a lot of information from this, and for non-commercial use you can download it for free and use it on Linux. But this one also exists for Windows, which also I believe AMD CodeXO does. There are separate activities in how to use profilers, so we'll move on to race conditions and talk some more about race conditions, because profilers are used to sort of optimize the performance of the program. Race conditions or race checkers are it's important to sort of remove race conditions for correctness. So race conditions occur when cores simultaneously access and modify a shared resource such as memory. So this can lead or will lead to wrong execution when you have many cores and you execute for a long time. So these are tricky problems to find, because typically when you have a small number of cores and when you don't run the code for so long, a program with data races can execute correctly. But when we are on it for a long time, and or if you have many cores, you exercise the system more heavily, and then you will typically find it. So either you find it by code inspection and you're good at writing your code, or you use tools, and then you use logs, atomic instructions, or resource replication to remove these data races. So here's an example. Here's a motivating example. So this is a code that calculates the value of pi. and the bulk of the execution time is in here, this for loop here. So what happens when we make this for loop parallel? Well, there is a race here. So the race is in the update of the shared variable area. So race condition is a non-deterministic behavior caused by the order in which two or more threads access a shared variable. So if you have two threads and they execute this statement, then you can have several things happening. So this picture illustrates one kind of interleaving of accesses. So you have thread 1 reading area here, modifying it, and storing back the new value here. And then you have thread 2 reading the value, modifying it, and then storing it back here. So this is an interleaving which leads into correct result. It could very well be that the interleaving was the following, that thread 1 reads and then thread 2 reads the same value. They both modify it and then write it back, and the second thread will overwrite whatever thread 1 wrote. So here we'll get a wrong value. Instead of 18 something, we'll get 15.2. And there's nothing in the system that will prevent this from happening. So this is a data race. Another kind of race condition is in this example when you have a single linked list. So you have a node which consists of a data element and a pointer to the next element. This is here. And you have the list itself, which is just a pointer to a head. And then you have a function add head here that takes a list to add a new node, and you'll have the list head to point to the node, and before that you take you take the list head and put it at the node's next pointer. So you put the new node at front of the list, right? So this is if you have a situation, you have the list that points to one node, and then this is only one node here, and then you want to add a new element, and I can have one thread that executes this statement here, which means that you have the next pointer pointing to the old first element in the list, and then a second thread comes and executes the whole thing before the first thread was finishing, which means that the second thread enters its new node here in front of the old node A, and then node B becomes dangling. Nothing points to node B so far, but thread 1 finishes the code, and when we let the list head point to node B, and now it's node C that's dangling here, and nobody will ever find it. So here we have a race condition also. So these are nasty problems because the programs with race conditions exhibit non-deterministic behavior, and you don't want non-deterministic behavior. Sometimes correct results, sometimes wrong, so it's tricky to find. So the way to avoid race condition is to scope variables to be private. If possible, you can use OpenMP private, and you can declare variables inside functions and so on. But in most cases, when you have real communication, you can't really do that, and you then need to ensure that you have mutual exclusion to data structures. So mutual exclusion is a kind of synchronization that allows only one single thread or process at a time to access to a shared resource, a data structure. And it's typically implemented with some kind of form of locking, but it could also be by using lock-free data structures. So a critical region is a portion of code that threads execute in a mutually exclusive fashion. In OpenMP, we have the critical pragma that you can use. So good thing here with critical regions is that they eliminate race conditions. However, if you have many critical regions executed, they sequentialize your program. And another bad news is that you need to identify these critical regions yourself. But let's see here how to solve the add head example here. Can we just take the update of head in a critical section? Well, let's see what happens. Thread 1 comes here, and you continue with thread 1 here, and then comes thread 2, adds its node here, thread 1 enters the critical region and finishes, and thread 2 enters the critical region and finishes, and we still have the same problem as before. This node here is left dangling. So in order for this to work, you need to protect both the read and write accesses here. So we put the critical region across both of these statements, the reading of the head and the storing of the head. Okay? This means when the thread 1 comes here, it can start finish putting the stuff in the list, and thread 2 has to wait until thread 1 finishes, and then thread 2 can finish, and then we have a real linked list with all the elements in place. Important here, use locks or mutual exclusion code to lock data, not code. You should associate critical regions to data structures. In OpenMP, there is actually a way to name critical regions if you want to have more. So you can have pragma OMP critical, and then you can put a name on it. So this is a parenthesis. You can say the name is list, and then you can have another called list 2. If you have 2 lists, then you can have one critical region to protect one list, and then another critical region to protect the other list. In OpenMP, you have an alternative to critical regions. You have the pragma OMP atomic. If you have a simple statement where you just update a variable, like in the Pi program, atomic is to prefer over critical because it's much more efficient. And this comparison here shows how it's different. So to the left here we have the pragma OMP critical. It protects this line here, but it protects the whole line, including the call to the function work1, and finding the value of index I and adding the index I to the result of work1 and so on. So in this case it means that basically the for loop here is sequentialized because of the critical region. If you use atomic, like to the right here, it provides an protection only for the update of the x of index I. So the calculation of index I and the calculation of work1 can be done outside sort of the protected code, and the update of x, which is this essential thing here, is the only thing protected. And therefore atomic here provides much more or better protection in performance-wise, but implementation-wise, actually OpenMP implementations can implement atomic by using critical, but nobody does this because of performance reasons. So data races are important to get rid of because a data race-free program behaves as if you execute under sequential consistency, and that is a much easier sort of programming model to reason about. Okay, tools to find data races. Intel Inspector is a good one. It's commercial, but it's free for non-commercial use on Linux. You have Thread Sanitizer from Google. It works with C, C++, and Go. You have Helgrind based on Valgrind on Linux systems. It's an open source tool which is useful for any kind of language. However, accurate data race detection is very slow and depends on the input data. It typically is based on sampling, which is not fully accurate, or code instrumentation, which is very slow. So you add, with code instrumentation, the tool will add some code on every load and store to shared memory, and then record if there could potentially be a data race for this particular input data. So code instrumentation is accurate, but it still then depends on input data. If the tool uses sampling, you can you know that if there is a data, if you find a data race, there actually is a data race. So there are no false positives, but you cannot really be sure that if you don't find it, that there are no data races at all. So this is the Intel Inspector tool. It can not only find data races, it can find memory leaks, memory corruptions, allocation, deallocation, API mismatches, and so on. But It's a very useful tool to find lots of memory problems. This is sort of how you use it on the computers that we use in the course here.